Tonight, at the feet of the statue of Sir Joshua Reynolds, a rocket lies in the forecourt of Burlington House, the home of the Royal Academy and of the Royal Society. It's here to mark the beginning of the greatest cooperative scientific venture the world has ever known. For 300 years, the Royal Society has been the focus of British science. It's acted as a centre for scientific information and discussion, and as a clearinghouse for scientific knowledge. It's been the patron of scientific enterprise. To be elected a Fellow of the Royal Society is to receive the greatest scientific honour that can be bestowed. Tonight, in the Council Chamber of the Royal Society, there are 3 scientists. On the right is the chairman of the British National Committee for the IGY, Sir James Wordie.
Good evening.
On the left is the senior secretary of the Royal Society, Sir David Brunt.
Good evening.
And in the centre is the president, Sir Cyril Hinshelwood.
Good evening. My colleagues and I welcome you to the Royal Society, where tonight, in conjunction with the BBC, we're glad to be able to tell you something about the International Geophysical Year. As the representative body of pure science in this country, we've had a good deal to do with the preparation of the IGY. And most of the fellows of the Royal Society are professional men of science, but not all. Indeed, our most eminent member is not. He does, however, know a great deal about it, and he is one of the most travelled men in the world. It is therefore most gratifying that His Royal Highness the Duke of Edinburgh has himself consented to tell for us the story of the IGY. I have the honour to ask His Royal Highness to introduce the Restless Sphere. In the next 75 minutes you'll be taken from the Arctic to the Antarctic and over the whole world by land, sea and air.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire.
War, argument and controversy are news. Peaceful cooperation is a bore. I think that partly explains why so little has been heard about the International Geophysical Year until quite recently. It is international because 50,000 scientists from 63 nations are taking part. And it is geophysical because it is a study of the physical properties of the Earth, its inside, its surface, and the atmosphere surrounding it. And at the same time, a particular study is being made of the sun, as it has a controlling interest in almost everything that happens here on Earth. For convenience, it's called a year, but in fact, the work will go on for 18 months. At midnight tonight, the greatest concerted effort ever made to observe and record the detailed facts of our world will commence. The present scheme was first suggested when 5 American scientists entertained a British colleague, Professor Sidney Chapman, at Silver Springs, Maryland. It has taken 5 years, careful organization and preparation. It will cost about £100 million. And although some useful information will emerge before the end of the IGY, it will take years before all the observations are tabulated and further useful information extracted. You would imagine, therefore, that there is some obscure scientific reason for all this, something to be taken on trust because it's obviously much too difficult to understand. Well, I hate to disillusion you, but the simple reason is curiosity. Mankind, and particularly the scientist, is tremendously curious. Gradually over the ages, the obvious questions have been answered, first by guesswork, and then by observation and theory, and finally by proof, with, in many cases, great practical results. But, odd as it may seem, we still know very little about the Earth. The deepest mines hardly penetrate the crust. Man has only managed to get a couple of miles below the surface of the sea, and only 16 miles above it. We don't know the Earth's shape accurately. We're not even certain that our maps show everything in the right place. We don't know the why and wherefore of the weather, of ocean currents, of climate variation and tides, of radiation, magnetism, and 1,001 other details of our planet. During the IGY, scientists from more than 60 countries will be putting their heads together in an attempt to find out.
Plans were made, and 5 years ago, things began to happen. An icebreaker pushed through the pack ice of the frozen Antarctic. At Delhi, in the heat of the Indian sun, some new equipment was hauled into position and survey work was stepped up. From Africa, a Nigerian came over to Britain to learn how to operate the equipment he would handle back in his own country. At Pribram in Czechoslovakia, in one of the deepest mines in Europe, scientists set up instruments to measure movements of the Earth's crust. High in the Bernese Oberland, in the observatory on the Jungfraujoch, cosmic ray studies were intensified. Here at home, Goffers at the Royal and Ancient at St Andrews saw a new shape on the horizon. In a listening post in New Zealand, a man studied the radio noises made by lightning. And way north in Canada at Fort Churchill, the foundations were laid for a high-altitude rocket research station. Whilst in Newfoundland, Canadian oceanographers plotted the route for a scientific sea voyage. In the Arctic, the Russians set up a base on an ice floe. In the Antarctic, the Americans built a camp at latitude 90, the South Pole. In Washington, a metal sphere was coated with a mirror finish, and the first satellite shell was ready for its journey into space. In Washington, in Moscow, in Prague, in Delhi, in Tokyo, and Geneva, all over the world, people made preparations. Brussels was chosen as the headquarters of the IGY, and Professor Sidney Chapman of Britain was elected president.
Good evening. I am speaking from the nerve center of the IGY in Brussels. It is from here that this great scientific venture has been organized. Now, the whole point of the IGY is intensive, continuous, and simultaneous observations all over the world. All through the IGY, we shall be paying special attention to particular parts of the world, such as the Antarctic and the tropics. You see, we'd rather understand some parts of the world really well than to know the whole of the Earth vaguely. Sir, we are keen to begin.
Well, Professor Chapman is much more competent to explain all this to you, but the information to be collected during the IGY falls into three broad divisions. First, the interior of the Earth, and this globe is cut away to show you, well, just about what we know about the Earth and its inside, which is not very much. But volcanoes and earthquakes give a clue, and these patches here show you the areas of volcanic activity all over the world. The second division is the surface of the Earth, and these arrows show you the circulation of the seas, and then at the top and at the bottom, the big ice caps of the North and South Poles, and the grid of longitude and latitude. And finally, the atmosphere which surrounds the Earth. You see our globe in the middle, with the weather inside that, and then finally the ionosphere. And 93 million miles away, the sun shines and makes the whole thing work. Now, there may be any number of separate sciences working in each of the three divisions, but the intention during the next hour, that is, if everything works, is to listen to some of the men from these different sciences and from different parts of the world, explaining their equipment and their work for the IGY. Now, I think it's most convenient to start with the interior and to work outwards. So first, then, to seismology, or the study of earthquakes, and we go over here to Vesuvius on the Bay of Naples in Italy.
And here, direct from San Sebastiano, a village at the foot of Vesuvius, you see the volcano. This is what Vesuvius means to us. Rubble, homes destroyed, by a living river of liquid stone that mercilessly burns everything in its path. Families disbanded, the very earth buried under fire. Here we live, in its shadow, and these crushed buildings are the remainder of a village built 3 times in 60 years, and a reminder of the volcano's power. Good evening. My name is Maurizio Pardi. I am bringing to you live television for the first time from the crater of Vesuvius. Everything is quiet now, but for the last few days we've been having terribly bad weather, and unfortunately we cannot bring to you all that we would like to bring to show you what the crater is like. A few days ago I was up here to shoot a film showing what the crater is really like. So now, here is the film.
Hello! Hello!
Good evening. I'm Maurizio Pardi from Radio Televisione Italiana. Excuse me if I'm a bit out of breath, but it's not very easy to climb out of an active volcano. Vesuvius is quiet at the moment. All that's happening now is steam escaping from fissures in the side of the crater. They indicate the intense heat that lies beneath the surface of the Earth. It's quiet now, but it may explode at any moment and bubble over. And then, who knows what may happen. Some spots on the crater wall are so hot that scientists claim that a pot of coffee will boil in 6 minutes and 20 seconds. Fried eggs are no problem at all. If the camera turns to the outside of the crater wall, you would see down there, beneath those clouds that are coming up, the ruins of the towns that were destroyed by eruptions in the past. Pompeii, obliterated by a particularly violent eruption nearly 2,000 years ago. The city was completely lost to us until comparatively recent times. This plaster cast of a young Roman woman taken where she fell was in fact only discovered a few months ago. Here she lies outside the old city gate. One of the most recent victims of Vesuvius is this village of San Sebastiano. More than 3/4 of it was crushed in 1944. Imagine the terror of seeing this stream of flaming rocks flowing relentlessly towards the village, creeping up and over the front doorsteps, flowing in through the backyards, absolutely beyond the control of man. All we could do was pray. To the left of this dark lava stream is the Osservatorio Vesuviano, the first seismological station in the world. Since Vesuvius has always been a threat, it was natural that earthquake research should begin here. In this observatory, the heartbeats of Vesuvius are recorded. If there is any movement in the earth, it shakes the drums. and the pens trace the direction and magnitude of the tremor. There are two kinds of tremors, like this one, which is what happened when Vesuvius erupted in 1944, or like this one, which is called a microseism, or little tremor. These occur even when there are no earthquakes, and it is on these little tremors that we shall concentrate during the IGY. Large earthquakes are also studied during IGY, and one of the countries mainly concerned with that study is Japan.
July the 1st is an important day in Japan. We Japanese scientists will be going to be very busy during the IGY because Japan plays an important part. Shigeji Suehiro, one of our youngest Japanese scientists.
Big earthquakes are our business. We Japanese have learned to respect them. Japan, you see, is in the middle of the most active earthquake region in the world. So, our studies here are important to us.
Each shiver is a direct message from the center of the earth. But we still know very little. We do not even know what causes an earthquake. What we do know is that the earth is made up of two main layers. The first one is about 40 miles deep, and the second one is about 1,800 miles deep. We still do not know what forms the center, but we think it is something like liquid. Deep down beneath the hills in this vault, we have our equipment. This tiny instrument, for example, is so sensitive that it magnifies a shiver of the earth 50,000 times. In the period of IGY, we are going to pay special attention to the very center of earthquakes. And in this way, we hope to discover what causes them.
That is typical of the whole IGY. Two nations on the opposite sides of the world studying the same problems at the same time. And their findings will be available to anyone who is interested. So much for the inside, now for the surface. There are 3,000 IGY stations dotted about the world. And about 250 of them are making a particular study of the properties of the surface of the Earth. In some of these observations, there is at least an obvious practical significance. For instance, glaciers are being studied, partly because they make up 10% of the world's land surface, but principally because they're melting away. And the sea level is rising at the rate of 2.5 inches a century. If they melted away altogether, the seaport cities of the world, like London and New York, would be completely submerged as the level of the sea would rise over 100 feet. The ice melts into the oceans, which cover 3/4 of the world's land surface, or world's surface. The circulation of the seas has a profound effect on climate. The sea provides great quantities of food, and in the future, it may become an important source of raw materials for industry. Obviously, the science of oceanography has many practical applications. Then there's the theory that the continents are slowly moving as if they were floating on a deeper molten layer in the Earth. It might be 1/2 inch a year, or even 1/2 inch a century. But this theory cannot be checked until the distance from London to New York or Cape Town to Sydney is known to within 50 feet or so. Only last month, the United States Air Force announced that after 4 years' work, they had finally pinpointed Europe in relation to America. So at last we know where we are. But there are many parts of the world where maps are still rather sketchy and inaccurate. These three sciences, then, glaciology, oceanography, and map-making, are the basis of the study of the surface of the Earth. First, glaciology. And what better place than the Antarctic, which contains the greatest area of ice in the world. Surgeon Lieutenant Commander Dalgleish was in charge of the advance party at the Royal Society's Antarctic base at Halley Bay on the Weddell Sea, marked there by a small flag. Here are his comments on life and work in the Antarctic.
As the summer sun rose over the Antarctic this year, 12 nations are setting up a total of 22 observatories. You may think that 22 bases in the Antarctic would make for a bit of a crowd, but in fact there are only 700 men there and a continent half as big again as Europe. This is the main Russian base at Mirny, and here is Little America, the first of several United States bases. Here is Magadan and the Totten unloading at Halley Bay, the main British IGY station on the coast of the Weddell Sea. The Commonwealth Transantarctic Expedition will also be doing IGY work. But before ships can get down to these regions, they have to push their way through miles and miles of heavy pack ice. These ships need to be strongly built for this work, with bows specially strengthened, either to cut through the ice or to push the floes on either side. Navigating through the ice is made a good deal easier with the help of helicopters and aircraft. But landing on the coast of Antarctica may be difficult, especially if you encounter 100-foot ice cliffs like this. In other places, however, there may even be a shore, and landing is much less of a problem. Man-hauling is only done when there is no other form of transport. It is still a good emergency method of getting stores in, but dogs are the great standby, the most constant, useful method of all when traveling across ice or snow. Crevasses must be carefully looked for, probed and bridged. This Russian truck broke through a weak patch in the sea ice, and the driver, Ivan Kamaro, died when his vehicle was lost. Unloading will take many days, but has to be done at high speed because the summer is comparatively short. It took us 6.5 days at Halley Bay to unload our 380 tons of stores and put them in dumps like this. That's myself unloading part of the 25 tons of coal in 90-pound sacks. The huts have to be built on large wooden rafts in place of ordinary foundations, as they're built on the snow. The whole of the huts themselves are prefabricated. All the timbers are pre-cut and carefully labelled so that anyone, whatever his job, can take part in this building. Last of all, the roofing felt goes over the whole thing to keep out the wind. As fast as stores are unloaded, they get covered in snow. All technical equipment has to be uncrated and connected up. The Met man down in Antarctica has to erect his 40-foot meteorological tower before he can start his observations and actually make use of his wind gauge and his wind direction indicator. The sunshine recorders have to be mounted in double rows because in the summer you have 24 hours of sunshine. And there's plenty to keep the surveyors occupied. Whole mountain ranges that have never before been seen are waiting to be properly located by star sites or sun sites. The Met man has the added difficulty of keeping snow out of his meteorological screen when the blizzards are blowing. Glaciologists measure the temperature of the ice below the surface in snow pits like this. Here is Dr. Paul Seipel, leader of the American expedition at the South Pole. All these observations that have been done in the Antarctic are the same as those made in many other places throughout the world. But of course, down there, they had to be carried out under far more difficult circumstances.
Well, not all scientists, as you saw, have the comfort of a laboratory. Now, as you heard, the greatest expanse of ice is here on the Antarctic and, of course, around the North Pole here. And it is the ice from these two regions which is melting into the sea, which is making the level of the sea rise. But ice doesn't only occur at the poles. There are, in fact, two glaciers here on the equator. But the ice is also melting in Europe. And so now we're going to Switzerland here, 11,000 feet up in the Swiss Alps to the Jungfrau Joch.
Good evening. Welcome to the Jungfrau Joch. This is the first time live television cameras have ever come up here. 12,000 feet. My name is Fritz Müller. I'm a Swiss geographer. I specialize in glaciology, which, unless you are a mountaineer, can be dangerous work. At At the moment, we are taking some scientific observations. Breathing up here is rather difficult. But from here, you get one of the finest views in Europe, the mountains of the Bernese Overland. First, the Vierschargabelhorn, and down below, the Aletsch Glacier, the largest glacier in the Alps. There you see a good example of a crevasse. And here is the Jungfrau itself. It's nearly 14,000 feet. Before we start work, we must make sure there will be no avalanche. Only yesterday there was a serious accident in Switzerland. At least 5 people got killed by an avalanche. Here we get rid of this danger by firing a rocket. Good, now we are safe. Here we are taking theodolite readings. By doing this, we can measure the movements of the glacier, which is really a river of frozen ice. The Aletsch Glacier below moves as much as 2 feet in one day, but last year it moved quicker. We don't know why. We hope to find out during the IGY. Here in this snow pit, we take the temperature of the ice, just as you saw Dr. Seipel doing it at the South Pole. Down the walls of this pit, there are different layers of ice. Each year, the snow produces its own layer like the rings in the trunk of a tree. By studying these layers, we can trace back important happenings in the climate of the Earth. Take, for example, the 1945 layer. It was formed when the first atomic bomb was exploded, and it contains a noticeable increase in radioactivity. In places, this glacier is over 2,000 feet thick. We can measure the actual depth of the ice by letting off an explosive charge.
Achtung! 1, Achtung! 2!
Here we record the shock waves reflected from the rock beneath the ice. And as we know the speed of the waves through the ice, we can calculate the thickness of it. Another thing we do is to see how long a block of ice takes to evaporate. 100 feet below where we are working now, there is an ice tunnel for research work. Recently, film cameras were taken down inside it for the first time, and Walter Plüss described the work there.
The sample is taken into this ice tunnel, which has been cut 100 feet below the surface. Here, it is shaped to weigh 3 kilos. After it's been hung for 7 months, it will shrink to this size, 1.5 kilos. And the shrinkage is due entirely to evaporation, not to melting. Also, the temperature in here does vary a little. It is, of course, always below freezing. Frequent measurements are taken of the size and shape of the tunnel. It was originally cut in 1954, and already it is getting smaller. This is due to the immense pressure of the 100 feet of ice above it and the ice around it. This means the tunnel is being twisted. Springs have had to be inserted in the cables to prevent same snapping. This tunnel is also used for testing equipment which will be used in Greenland by the IGY expedition. During the IGY, the Swiss will also be doing special work in Greenland. We will be parts of an international team of French, Austrian, German, and Danish scientists. Why bother about these cold areas? Well, for the last 50 years, the glaciers have been receding and the high snow is melting. The levels of the ocean have been rising. If all the glaciers melted at once, the water would rise halfway up Nelson's Column.
Sir, you are now on board Her Majesty's Canadian ship the Lisgard, 200 miles off the coast of Nova Scotia. My name is Dr. H.B. Hashey. I am Chief Oceanographer to the Fisheries Research Board of Canada and responsible for the programs carried out under the Canadian Joint Committee on Oceanography. From these studies, we hope to learn more of our coastal water in relation to such matters as fisheries and navigation. The last water bottle is coming over the side. What you see here is an Anson deep-sea reversing water bottle with 2 deep-sea reversing thermometers attached. The oceanographers are removing the bottle and taking it into the lab. Here in the lab, we see the temperatures being read and recorded, and the water samples being drawn off for analysis.
This is the first time in history that such tidal observations are being made simultaneously all over the world. Oceanography demands cooperation, and Canada will extend this cooperation as the IGY program gets underway.
From oceanography to geography. And the grid for map making is latitude and longitude. And this grid is locked at the poles. Unfortunately, the Earth is wobbling about slightly inside this grid, which makes the whole thing slightly inaccurate. And this wobble is one of the problems being studied in England. Dr. Atkinson will explain how this movement is measured in relation to the fixed stars using the zenith tube and its camera here at Greenwich.
Here we are at the Royal Greenwich Observatory at Hurstmonceux in Sussex. Down below me is the castle itself, which was built in 1440. The observatory, when it was founded in 1675, was in Greenwich, but we've come away to the clean air and clear skies of Sussex. And behind me here, the photographic zenith tube, the special instrument you've come to see. Here we are at the control console itself, which works the instrument. It carries a large number of little telltale lamps to keep the observer in touch. At the console, I have a list of stars with a time for each. 76 seconds before any given star is due, I simply press this button and the instrument takes charge. Next day, the plate is developed. This little square of glass is one of the photographic plates, and the 4 little dots on it, which are the 4 pictures taken of that star, are very precisely measured up in a special machine. Nowadays we know that the north and south pole of the Earth are not 2 completely fixed points on the surface of the Earth. They wander around over a small area, perhaps 50 or 60 feet across. And this appears as a variation of latitude at all stations throughout the world. Somewhat similar observations to these are being made at a number of different observatories during the International Geophysical Year, and in particular at the observatory at Dehradun in India.
The foothills of the Himalayas is a good place for star observations. The air here is cool and very clear. Here we study the odd wobbles of the Earth as the Earth shakes on its axis. To do this, we employ a technique very different from that of Greenwich. This is a transit telescope. Through it, we track the stars as they cross our meridian. It is like watching a runner past the winning post. Inside the eyepiece is a thin line which represents the meridian. As the star crosses this line, the time is automatically recorded on this drum. From these lines, we can work out how fast or slow the clock is. During RGY, we'll be taking similar observations for 430 nights and then calculate how much the Earth is wobbling on its axis.
You've seen something of the sciences which deal with the interior and with the surface of the Earth, and now to the most important of all, the atmosphere and the sun. And here, in this inner globe, you can see perhaps those white arrows which show the general circulation of the wind. And this inner ring here shows the upper limit of our weather and the clouds. And this outer ring is the ionosphere, and we'll come back to that in a moment. The weather is always with us. Violent storms have a habit of springing up from nowhere. Their origin is a mystery, and their end is equally unpredictable. Sometimes they are harmless enough, but others can cause frightful damage. You only have to remember the devastation caused by the West Indian hurricanes. And only yesterday we learnt of the disaster in Louisiana caused by Hurricane Audrey. And in Europe they've been having most terrible storms as well. And we, after all, are not altogether free from the problems of the weather in this country. Tonight, the outside broadcast cameras are at Crawley in Sussex. And this is one of the Met stations in this country which is trying to find out what new surprises the weather has for us. So over now to Crawley.
Well, sir, it's easy enough to tell you what the weather is doing here at the moment. Our problem is, of course, to know what it's going to do in the future. At this meteorological station at Crawley, it is, of course, only one of many taking part in the International Geophysical Year. It's set in the rather lovely Sussex countryside here and is one of 8 special upper air stations in the United Kingdom. It's from here that we release these meteorological balloons, not infrequently mistaken these days for flying saucers. In order to forecast the weather in this country, we need to have a knowledge of the weather over a large area of the Northern Hemisphere from observations from land, sea, and in the air. But all those observations will contain 4 basically, well, fundamentally important measurements. They are, first of all, barometric pressure, which we measure on a barometer, which looks like this. It's probably a good deal larger and certainly more elaborate than the one you may see at your hall at home. I see that standing at fair, but by the clouds on the horizon here, we're in for a thunderstorm very soon, I feel sure of that. Well, temperature we measure always in the shade. So we've constructed a special box in which we enclose our thermometers, which give us not only temperature but humidity too. Well, this box, I think you must admit, looks rather like the latest thing in beehives. But with the slats all the way around it, it allows the air to flow across the thermometers, and so we never measure the temperature of stagnant air. The temperature at the moment, incidentally, is 78. It's very close, and there's not much wind, as you see by the wind masts there, and the anemometer cups rotating only very, very slowly. Well, these measurements are, of course, made on the ground, and we need to know the very same measurements only high above the surface. To get this, we use what we call a radiosonde balloon. Now, this apparatus is what we call a radiosonde, and we attach that to a balloon and send it high into the stratosphere. Inside, we have a very small radio transmitter, and in the bottom, batteries to operate it. Grouped around the outside of that are 3 instruments. One for measuring pressure there, just going on there now, one for temperature, and another for humidity. Now, as this apparatus is carried upwards by the balloon, the wind rotates that little windmill on the side, switching each of the instruments in turn to the transmitter, which sends back to us here at Crawley a note. And from the pitch of that note, we can tell just what those 3 instruments are reading. Now, my colleagues are about to release one of these balloons, and there you see the hydrogen balloon already filled and about to be taken out. One of the chaps will be walking across now with the small radiosonde unit, and he's going to fasten that, of course, onto the end of the balloon.
Right.
Now, immediately below the balloon, we have what looks very much like a kite. That is a radar reflector. For by following this balloon with radar equipment, with radar scanners, here you can see them there now, we can, of course, compute the wind speed and direction. So one way or another, we get a lot of information from this balloon. Well, as the balloon goes up, you see the transmission signals are already coming through to us down here. And there's the scanners following the radar reflector. Well, the balloon will, of course, eventually burst. Often at a height of 17 miles, but don't worry, you're not likely to be hit on the head with one of those transmitters falling from that height, for it all comes down very gracefully by parachute. We lose a lot of this equipment, of course, but much of it is recovered. There is a little ticket on each transmitter offering exactly 5 shillings reward if it's returned to us. So not only do we get weather information from it, but also it's quite a treasure hunt for school children. Now the signal's coming down through this receiving aerial to the operations room here at Crawley, where we have the instruments for receiving the impulses. Well, there the operator is reading the frequency of the notes in cycles per second, and they're being handed over and converted into measurements of pressure, temperature, humidity. Well, we release 32 of these balloons from the United Kingdom every day, and thousands, of course, are released throughout the world daily. During the International Geophysical Year, on special days, which we're calling World Days, hundreds of these upper air stations will be releasing balloons to make special observations. They'll pass the information to Geneva, to the World Meteorological Organization there, where scientists will compile that information onto cards no bigger than the size of a small postcard. That small postcard will contain information about the world's weather all over the world on that one day. In this way, we hope for the first time to study the weather affecting the Earth as a whole, and who knows what advances we may not make in weather forecasting as a final result of this coordinated study of the atmosphere.
But controlling all the Earth's atmosphere, weather, and radio conditions is the sun. Throughout the IGY, scientists will be keeping a constant watch on the sun. In the Soviet Union, in America, in Czechoslovakia, and in other observatories all over the world. This is what they see, flares leaping from the edge of the sun's disk. And when they direct their new radio telescopes onto this outburst, this is what they hear. These solar disturbances have quite serious effects on the atmosphere of the Earth. And so far, these outbursts are quite unpredictable. Every 11 years, the sun seems to suffer from an attack of measles. And in fact, the IGY was chosen to coincide with the peak of this sunspot cycle.
Solar outbursts are often accompanied by a sharp increase in the intensity of the cosmic radiation. This is a stream of particles continuously bombarding the Earth, and is one of the problems which we in Bristol University propose to study during this geophysical year. We plan to fly small packs of films to great altitudes on free balloons. These photographic emulsions will record the passage of each cosmic ray particle in the form of a line of silver grains. Inside the balloon shed at this Royal Air Force Station, we are preparing to fill one of our balloons with hydrogen gas. The study of some rare events has made necessary the use of very large stacks, and to lift these stacks to high altitudes, we have developed a technique of using large plastic balloons. This balloon is manufactured from polyethylene sheet, 1.5 thousandths of an inch thick. Only a small part of the balloon is inflated on the ground, but as the balloon rises, the gas expands until when the balloon reaches 100,000 feet, that is about 20 miles, the balloon measures about 200 feet long and 70 feet across. These balloons weigh 250 pounds and are capable of carrying about 250 pounds of load. The equipment is outside on the field, being prepared. It's being tied onto a long cord, ready to be hooked onto the end of the balloon after filling is completed. These clockwork mechanisms will burn through the nylon cord. At a predetermined time, the equipment falls by parachute, and its fall is followed by several radar stations using this reflector. The canework frames serve to protect some of the equipment from damage on landing. The small frames contain the radio transmitters. This antenna behind me is the receiver of one of these transmitters. The large frame supports the most important part of the experiment, the sensitive films which record the cosmic ray particle. Well, I can see that our balloon is now ready to be launched, and I must listen to the signals from the balloon.
One, go! Mind out the way, mind out the way! Get out!
Here is another solar flare. 24 hours after one of these outbursts, the particles ejected from it cause an aurora, or as it's sometimes called in this hemisphere, the northern lights.
One of the ways of recording the northern lights is using this instrument, which is called an all-sky camera. This dome-shaped mirror here reflects the whole sky into this mirror at the top and then down through this hole into the lens of a cine camera, which is fitted inside here. And to give you the idea of what this thing looks like, we put a television camera, turn this on its side, and put a television camera in the end, so that you can see the sort of effect it has. And there you can see more or less the whole set. The thing at the bottom, below the middle, there's somebody walking about. If I wave my hand, perhaps you can see me just to the left there. And now I'm going to show you a piece of film showing one of these cameras being installed. And this film shows a camera being installed in Murmansk in northern Russia. There's the mirror again, and there's the camera going in at the bottom. And those are the sort of photographs it takes. These photographs are taken every 4 minutes or so, as you can see by the clock buzzing round in the bottom right-hand corner. And that is a very much speeded up version, but shows the whole aurora forming and spreading over the whole sky. But a more usual way of observing the aurora is by eye, because it's the only way in which the whole display can be observed from beginning to end. But let me introduce Mr. James Peyton in his observatory on the top of his house at Abernethy in Scotland.
My name's James Peyton, reader in meteorology in Edinburgh University. My main job is the coordination of European visual observations of aurora. Naturally, I want to see every aurora that may become visible from my house here in Perthshire. So I've just had this small observatory built into the top of my house. My family call this place the Gods, and I'll be sleeping here on this bed on every night during the geophysical year. The situation here is ideal, a clear and uninterrupted view all round to the distant mountains, from Ben Vorlich in the west to the Sidlaw Hills over the Tay in the north and east. This is the camera. It's very simple, but has great light-gathering power. We make exposures by knocking down the shutter. This way, one can work with gloved hands in cold weather. Then we can take 6 pictures on each plate by moving the lens here. Now, when an aurora suitable for photography appears, I get into touch immediately by telephone with colleagues near Newton Stewart, Hull, and Newcastle. Hello, Charles Wilson. Are you there?
Newton Stewart here. Hello, Mr. Peyton.
Direct on the arc near Polaris.
Ready? On Polaris.
On?
On.
Off.
Off.
That was plate 6, exposure 5, on the arc near Polaris, 22, 31, 27, 22, 31, 42. Well, we'll finish off now, Charles Wilson.
Good night, Mr. Peyton.
Goodbye. But our main work consists of a study in the Balfour Stewart Auroral Laboratory of Edinburgh University of the development and decay of each aurora that's seen over Europe, from the Arctic, sometimes as far south as North Africa. In this work, we're dependent on the observations of meteorologists and of scores of amateur observers. During the geophysical year, observations will come in from all over Europe to Edinburgh, where they'll be plotted on a chart and their minute-to-minute development studied.
Beyond the aurora is the ionosphere, and the aurora takes place in between this ring and this outer one. And the ionosphere is a layer of electrified gas all round the Earth. And without the ionosphere, long-distance radio communications would not be possible. Radio engineers aim their transmissions in such a way that it bounces off this ionized layer back to the receiving station, rather like a billiard ball bounces off a cushion into a pocket. The trouble is that these layers have a habit of moving up and down. When a solar flare occurs, the layers are intensified and absorb the radio signals. And this causes a radio blackout and throws world communications into chaos. At the moment, the radio engineer is rather in the position of a billiard player using a billiard table with moving and sometimes non-existent cushions. In fact, he would dearly like to know a bit more about the ionosphere.
Sir, this is Africa. We are in the Belgian Congo. These are the people of the Bashi tribe. They live in what some call Darkest Africa. Yet on a short distance from the Bashi tribe, there is a large scientific station. This is where I work.
During the IGY, scientists all over the world will be aiming radio signals at the ionosphere, measuring their reflection and then attempting to plot its precise movements. These reflected signals show up on cathode ray tubes.
29, 31, 26,
26, 34,
26, 34,
34, 32,
31, 29, 35, 28.
In Japan, we are doing the same work as in the Belgian Congo. This film is of the ionosphere. It is 6 in the morning, no sun. Now sun rises, layers grow. Now at 1:40, a solar flare occurs. Watch what happens. Disappear, radio blackout.
In the Soviet Union, too, we shall be studying the ionosphere throughout the IGY. Our neighbors in Czechoslovakia are also playing their part.
You are looking now at the largest steerable radio telescope in the world. I expect that many of you will have recognized it as the one we're building at Jodrell Bank, near Manchester. The project has been in hand for about 7 years now, and before the IGY is very old, we hope it will be completed. My name is Lovell, and I'm the Professor of Radio Astronomy in the University of Manchester, which means that I'm the director of this establishment at Jodrell Bank. Some of you are probably wondering how radio receivers and aerials help in astronomy. It rests on the discovery that radio waves, as well as light waves, are reaching the Earth from outer space. One of these radio sources is so distant that the radio waves have taken 200 million years to reach us. Much of our work at Jodrell Bank deals with the exploration of these remote sources. For example, this aerial is always trained onto the radio source in Cassiopeia. The strength of the signal is recorded continuously by a pen recorder. Sometimes the records show that the signal is varying rapidly in strength. In another of our programs, we record the entry of shooting stars or meteors into the atmosphere. To do this, we scan the sky with our own radio beam, and you can see the echoes from these meteor trails on this CRT. In another of our IGY programs, we send out radio signals to the moon and receive them back again. The echoes from the moon sound like this. It is incidentally on work such as this that the giant telescope which you saw at the beginning of your visit will be used. Its true role lies in the exploration of outer space. Later on, we may use it for one or two special IGY experiments. I expect that one of its tasks will be to track the American Earth satellite as it circles round our planet, although the closest it will come to our shores is the coast of Spain. A cooperative program between the Jodrell Bank telescope and the satellite might well give us unexpected and valuable results for the IGY.
I wonder if Cassiopeia is receiving this program. One of the greatest snags in studying this world lies in the fact that we're on it. Observers can't see it from the outside, and it has always been a problem to find out just what is going on outside. That is why the most interesting instruments of the IGY are the rockets and satellites. They'll go high into the atmosphere and give a radio running commentary on the Earth's envelope at a height of anything up to 1,500 miles. The satellite is our first step into outer space. This thing, although it's only a little bit bigger than a football, may well reveal many things about our planet which up till now scientists have only been able to guess at. But now let me introduce Dr. Lloyd Berkner, world reporter on rockets and satellites.
Since the first V-2 rockets were launched during the last war from Holland, rockets have assumed a much more peaceful application. They are now used for high-altitude sounding and exploration of our outer atmosphere. The work on rockets started at White Sands soon after the war with the firing of V-2s carrying instrumentation to explore the atmosphere. But since that time, the rockets have developed into much more sophisticated equipment, and only a few weeks ago, there was fired from White Sands, New Mexico, the Aero-B High, a model of which I have here in my hand. This Aero-B High can carry very complicated apparatus to view the sun, for example, from outside the atmosphere, to measure the ultraviolet and X radiation which does not penetrate it.
I am Dr. Richard Towsey, a physicist from the Naval Research Laboratory in Washington, D.C. The experiment that we plan to do is to study the sun in the extreme ultraviolet. In cooperation with observatories on the ground, we expect to learn a great deal about the atmosphere of the sun, and the data that we obtain will bear upon the processes which take place in our own atmosphere. This experiment is the forerunner of 3 which we plan to do during the International Geophysical Year. Astronomers all over the world will have a chance to compare data which we may obtain in the extreme ultraviolet with whatever measurements and observations they make on the sun at the same time. We came to the White Sands Proving Grounds about a month ago to integrate the equipment into the rocket, test all the circuits, make sure everything was operating properly. Last night, we've installed our equipment for the last time in the rocket. Saw it placed in the firing tower. Then we relaxed while the crew was fueling the rocket.
Good morning. I'm Chief Radarman Jerry Hudnall, Airby Rocket Chief of White Sands, New Mexico. The reason for my rubber suit that I'm wearing is that we're using a highly toxic aniline fuel and a red fuming nitric acid, and we have to have the suit for protection. Now, this morning, the winds are good. At 0630, we will launch this missile into the air at 135 miles.
Chief, you prepare the missile for fueling?
Yes, sir.
Stand by. Mark 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
In Japan, the Japanese have designed the Sigma and the Kappa rockets to make measurements along the 140-degree line in the opposite hemisphere from the Australian and British measurements.
This, sir, is one of our Japanese rockets, which we have built specially for the IGY. This one is called a two-stage Kappa rocket. The big rocket will reach a height of 10 miles. Then the small one will be fired and travel on up to 80 miles. During the IGY, we in Japan will be using these rockets to carry up the instrument to measure such things as atmospheric pressure, temperature and wind, solar radiation, and cosmic rays.
はい、60秒前。50秒前。10、9、8、7、6、5、4、3、2、1、0。
Recently, I had the opportunity to visit the Great Rocket Range at Woomera in Central Australia. Here, the Australians and the British, working jointly together, will launch the British Skylark rockets to make measurements in the outer atmosphere in that region of the Earth.
This is the Woomera Rocket Testing Range in South Australia. My name is Tom Cook, and I'm in charge of the preparation and firing of a Skylark upper atmosphere sounding vehicle. This vehicle has been designed by the Royal Aircraft Establishment in Farnborough and is to be used for experiments at altitudes from 70 to 90 miles during the IGY. These experiments will be used to determine the temperature and pressure at various heights and to study such other phenomena as day and night air glow.
All posts from Sub 1, information on the Skylark firing. The round will be fired from the Skylark launcher on apron number 2. Line of fire 313 degrees, QE 75 degrees.
Doppler ready.
Doppler ready.
Telemetry ready.
Telemetry ready.
Contrast ready.
Contrave ready.
Vinton's ready.
Vinton ready.
Kinney's ready.
Kinney ready.
Timing section ready.
Timing section ready.
Smoke rockets will be fired at -2 minutes and -10 seconds to enable the wind structure to 1,000 feet to be obtained.
20 seconds. 15. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
altitude sounding rockets will, of course, be of very great scientific importance during the International Geophysical Year. But there will be other rockets, such as this, which will launch the instrumented Earth satellite. The satellite will describe an inclined orbit to the Earth's equator extending from about 40 degrees north latitude to 40 degrees south latitude. And, of course, the Earth will rotate under the orbit so that the orbit will appear to regress around the Earth. The satellite itself is instrumented as indicated in this model. Here will be the apparatus, including the batteries and the scientific equipment to make the measurements and to radio the information back to Earth. Moonwatch is the word we use to describe the program for tracking the satellite with thousands of amateur observers located in many parts of the Earth.
My name is George Pickard, president of the Wakefield High School Rocket Society. This is the South Arlington Moonwatch team in Arlington, Virginia. We are a student organization to foster scientific investigation of rocketry and astronautics. This is a rehearsal.
My name is Dave Saldus. I'm sponsor of this group and responsible for the technical details. The boys have aligned their telescopes so that they're covering a straight north-south line across the sky. The position of the satellite will be noted as it crosses this line, as well as the time of transit. That's the significance of the in-out signal that you will hear an observer call. In! Out! This information will be transmitted to a central headquarters at the Harvard University, Cambridge, Massachusetts, where it will be correlated with information from other Moonwatch teams, finally fed into a central computer which will figure out the orbit of the satellite.
This rocket will be fired, and the first stage will separate at a height of about 30 miles or a little more. The second stage will carry the satellite to the full altitude, and then the second stage will separate away, and the third stage will launch the satellite to full velocity so that it will then be in orbit. The satellite will be launched by means of this rocket from the Patrick Air Force Base in Florida sometime early next year. The United States Earth satellite will be launched by means of a three-stage rocket that is now being assembled at the Glenn L. Martin plant at Baltimore, Maryland.
My name is Elliot Felton. I am the operations manager for Project Vanguard, responsible for the design, manufacture, and test of the three-stage rocket vehicle which will carry the scientific Earth satellite into space. One of the items which you can see here is a complete first stage assembly, which consists of the rocket engine, the two fuel tanks, and a spacer section to taper down the diameter from the 45 inches of the first stage to the 32 inches of the second stage. In another area, you can see a second stage being assembled. This assembly consists of the fore and aft ends and the aerojet section which fits in the middle. We have some other scenes of the nose cone of the rocket vehicle. It is a plastic nose cone to protect the satellite ball itself during flight through the dense atmosphere. The vehicle is moved to our vertical test tower. This is the first time the entire vehicle is mated together. And at this point, we can more closely duplicate the final testing of the rocket in the field prior to launch.
After living and working with this thing from the beginning, I'd sure like to be the man to fire.
I quite see his point of view, but I'm afraid that was not the complete rocket being fired. It was, in fact, the first and third stages being tested in May this year. This attempt to find out about the Earth through the electronic ears and eyes of these rockets and satellites seems to me to be the most fascinating part of the whole IGY. Since the beginning of time, the world has never been seen as a planet, and it's only a matter of time before a manned satellite becomes a possibility. And that'll be a step to what? Your guess is as good as mine. But let's stick to facts. The satellite is expected to buzz around the Earth at 18,000 miles an hour on an elliptical course. This will take it 1,500 miles away at its furthest and 200 miles at its nearest point to Earth. And this is what you would see if the BBC could get a television camera a couple of hundred miles above the surface of the Earth. At this particular moment, it's over the surface of the sea. But here you see Japan and Asia coming up. That brings us to the end of this survey of IGY. And it only remains for me to add that all the facts collected during the next 18 months will be filtered into and stored in 3 world data centers. One of these centers is international, with each nation taking the responsibility for one or more sections. The 2 other centers will each take a complete set of data. One will be in the United States of America and the other in Russia. The IGY is the world studying itself. It is also much more than that. It is a great experiment in world cooperation. It's seldom that mankind acts in harmony, but the 5 years' preparation for the IGY alone is solid proof that we are capable of working together if we really want to. The measurements and observations, the expeditions and experiments will do much to satisfy scientific curiosity. We can also look forward to far-reaching practical results, which will improve the material well-being of the peoples of this world. But, and perhaps most important of all, the international cooperation of the next 18 months may well prove to be the first tentative step to a friendlier and a more tolerant feeling between the nations of the world. The International Geophysical Year begins at midnight. The great adventure is about to start.
5, 4, 3, 2, 1, 0.
Nature that framed us of 4 elements, warring within our breasts for regiment, doth teach us all to have aspiring minds. Our souls, whose faculties can comprehend the wondrous architecture of the world, and measure every wandering planet's course, still climbing after knowledge infinite, and always moving as the restless spheres, will us to wear ourselves and never rest, until we reach the ripest fruit of all, that perfect bliss and soul felicity, the sweet fruition of an earthly crown.